if you check my video, yeah, please subscribe. So normally this series, and for a couple of days later on, I'm gonna prepare all the topological problems in Leetcode. So firstly, I'm gonna start from the medium problem, and then I'm gonna try the hard problems. Yeah. Now let's try to solve this problem, 310, minimum hit trees. So let's first understand the problem. A tree is undirected graph. So for this problem, it is undirected graph. Yeah. So with any two vertices are connected. So a tree, basically it is a tree, but currently it can become a graph. It is undirected. Yeah. So in other words, any corrected graph without simple cycle is a tree. So if the graph without a cycle, so it's gonna be a tree. So given a tree of n naught from 0 to n minus 1, so this is clear, 0, n minus 1, yeah. This is the vertices, and the edges is n minus 1. And this should also be clear, because this is a tree structure. If the vertices is n, so the number of the edges is going to be n minus 1. And for each edges is I, going to be ai and bi. So it means the two vertices connected to each other indicate it is an undirected edge between two nodes ai and bi in the tree. You can choose any node of the tree as the root. So if this is a tree, you can choose any node as the root, right? So when you select the node x as the root, the result tree has height 8. So for example, if we choose this root, so for the graph, so for the tree structure, we have a height, it is a 2. Yeah, because this is the 0th layer, first layer, and second layer. Yeah, because for the first, we're going to call it 0 layer. It is dependent on the problem, of course. Maybe you think this is going to be 3 layers, but for our problem, it is actually 2 layers. The height of the tree is going to become 2. Yeah. So from here, the height is 1, and to here, the height is 2. When you select a node x as the root, the result of the tree has height 8. Among all possible rooted trees, those with minimum height, going to call the min 8. It is okay. are called minimum height tree. So we're gonna check this MHT. We're gonna check all the minimum height trees. Yeah. So we're gonna return a list of all minimum height trees root labels. You can return the answer in any order. So this is okay. We need to find all the root node which has the minimum height tree. So for example, for this tree structure, the height is 2. We need to find this kind of node. Yeah. But for some kind, for example, for the first example, this example, the minimum height of the tree is 1 and the root is 1. It is okay. But as you can see for the second example, there are going to be 2 nodes. So the minimum height of the tree is 2, and we have 2 nodes. It is 3 and 4. Yeah. So this means it may have many vertices we need to return. Maybe you're gonna think about why not just try to use brute force to solve the problem. Basically, we're gonna check one node by one node. We're gonna check n node. It's gonna be 0 to n minus 1. We're gonna check all the nodes, and for each of the node, we're gonna use DFS or BFS to check the depth of the tree. But in this way, the time complexity gonna be so the number of vertices n times m plus n. Yeah. So if you are checking the number of n, it is 2 times 10 to the power of 4. It means 10 to the power of 8. Basically, it cannot pass. Because for Leetcode 10 to the power of 8, basically it is a very large number. If you pass it, maybe it is nearly to the time limit exceeded. Yeah. So this means this is not the right way to solve the problem. We have to find a clever way to solve the problem. Yeah. So if you check the structure, check this kind of tree structure carefully, you're gonna find something. So let me just make another drawing. So let's just make a drawing. So this is a tree structure, and it is connected bidirectionally, and it's gonna be connected like that. Yeah. So currently we don't know which is gonna be the root of the tree. Yeah. But what is the clever way to find the height of the tree? So this means if we have a tree structure, we can always check the node which has no children and we're gonna take out this children, and then we're gonna check the next layer. We're gonna check layer by layer, and in this way we can find the depth of the tree. Let me make a drawing. So firstly, we're gonna check the last layer from here. Yeah, maybe I'm gonna make another color. And then we're gonna check this layer. So this is for example, this is layer 1, and this is layer 2, and then we're gonna check layer 3. We're gonna check one by one. Why we can use this way to solve the problem? Because this is a topological sort. For the topological sort, we can always check this layer first. If there's some parent, then we're gonna check the next layer. Until here, it is the root node. It means this is gonna be one of the possible results. Yeah. Maybe there are some other ways. So for this kind of a structure, yeah, we need to make the drawing totally like this to make it work. So first of all, we're gonna check this layer. It's gonna be 0, 1, 2, and 5. Yeah. And then we're gonna check the second layer. The second layer is gonna be 3 and 4. So we're gonna just need to put 3 and 4 inside of a result array. As you can see, it is not so difficult if we are using the topological sort. We can solve the problem directly if we can recognize the problem as a topological sort. So how can we put the result? How can we put it inside of a result array? And we just need to use the BFS to check. And for each of the queue, for each layer of the queue, we just need to put the queue inside of the result array. And finally, we just need to return this result array. It's gonna be easy. Yeah. Now let's try to solve the problem. As I always did, I'm gonna prepare a graph and integrate. So the graph is gonna be a default dict with a list. So this is gonna be adjacency list, and integrate is gonna be 0 times n, the number of vertices. But for this problem, it is a undirected graph. This means we need to tackle both ways. I mean AB and BA. And for the integrate, it is also we need to check the integrate of vertices A and vertices B as well. So I'm going to check all the edges first. So for AB inside the edges. So for the graph, I'm going to prepare an undirected graph. So it's going to append B, and B, I'm going to append A. And similarly for the integrate, so for the integrate A should plus equal to 1, and integrate B should plus equal to 1. So currently, while we are checking the integrates, it's going to at least have 1 because it is undirected. So for example, this is 0, 1, 2, and 5. So the integrate for those nodes is going to be 1, not 0. Yeah, because currently it is undirected. If it is directed, it is 0, okay? Now, we are going to prepare the queue. I'm going to prepare a DQ as always. So I as the node. So for I, they enumerate the integrate, and I need to check if this number of the integrate equal to 1, not 0, because this is undirected graph. And for the result, yeah, currently let me just give an empty array for the final result. Yeah. Now let's just try to use the BFS to solve it. So while q, but for this one, I'm gonna check layers by layer. So I'm gonna use an underline in range length of the q. So I'm gonna pop it out. So the node gonna be equal to q.pop left. Yeah, why I need to use this kind of structure? Because I need to check the layers layer by layer, because I just needed to get the last layer. Yeah. So while I'm checking each of the layer, I pop out this node and I check the neighbors. So for neighbor ing with this node, yeah, and I can check the integrate. So integrate with this neighbor would minus equal to 1, and I gonna check the integrate with this neighbor, but currently it is not 0, it has to be 1 because it is undirected. Yeah. Although I said it many times, but sometimes you might forget because if you didn't know about the structure. So if this integrate becomes 1, definitely we can put something inside the queue. Yeah. Now this is the basic structure, but we didn't get the result. So for each of the Q, it might be a possible result. So result gonna be the list of this Q. Yeah. So if it is not, I'm gonna check the next layer and the next layer until I get the last layer, and the last layer gonna be my result. And finally, I can return the result. So this is the possible case if everything's okay. But sometimes, for example, if the number of the node is 2, and I have a node 0 and a node 1, but they are not connected, what should I return? I need to basically return an array with 0 and 1. But currently, according to my design, I'm going to return an empty array. So this is not my answer. So this means if I were to return a result, the result must exist. If it is empty, definitely, I'm going to return all the numbers of the nodes, because there's no connections with the node. So it is always separated like that. 0 and 1, they are not connected for each of them. Maybe this is 2, and they are not connected. So I'm going to return all of them. Yeah. So if a result exists, else I'm going to return all of them. So Leetcode going to range with the number of vertices. Yeah. So this is going to be the entire code. As you can see, it is much clean and concise. Yeah. So I know I solved this problem before, but maybe it is not the best way. I think this one might be the best way, and it is much cleaner and concise for the code, and it is very clear of how to solve the problem. Yeah. Now let me just run it to check. For neighbor in G node, I did something wrong. Let me check. Collections unhashable collections DQ. Let me check. This is my graph, and this is the integrity, and here I get the this is the result. So for anything inside the Q, I'm gonna pop it out. So for neighbor in G node, yeah, why I get a Q? It should not be a Q. Yeah, let me just print out what is neighbor. What is the neighbor? Yeah, let me just print out this this G with this node. I don't know what is inside. 111. Yeah, it seems it is okay, but unhashable type collections dot DQ. Why unhashable? I don't know, but let me just print out the graph and the Q to check if I did something wrong on the graph and the integrity. Yeah, because I definitely don't know what is wrong with it. So this is my graph with this example 1 connected to 0, 3. It is okay. So this means my graph is okay, and the integrity is also okay. So currently here everything is okay. And let me check the Q. This is my Q. I put everything inside the Q, and the result is going to be empty. Yeah. Let me just check the Q as well. Yeah, because this is just confusing. 0, 2, and 3. It is okay. This is inside my Q, and the result would get the list of the this Q. So for here, for anything inside the Q, in this Q, I pop out the node, and for neighbor, inside the node. For neighbor in G node, unhashable type. Yeah, I really don't know what happens. Unhashable type for neighbor in yeah, maybe something about here. Let me just check it carefully. If the integrate neighbor would minus 1 if this equal to 1. Yeah, I did something wrong. As you can see, Q should append a neighbor, but I use a Q append a Q. So this means why it is a collection the Q, because I put a value as a Q inside my Q. Yeah, so Q is just like an array, and I put an array inside a Q. This makes the problem really difficult to debug, so I have to type carefully. Now let me just check. As you can see, it works. Now let me just delete the print and submit it to check if it works. Yeah, as you can see, it works, and it's pretty fast because the time complexity becomes O(n). Yeah, just before it is n squared if we use brute force. Now we are using the BFS. It is the number of vertices plus the number of edges because they are equal. So the time complexity are going to be O(n). Yeah. So this is for the problem minimum hit trace. Thank you for watching. See you next time.